Is it working? Yes. Okay. So our first speaker is Michael Grieve. So Dr. Grieve is the executive director and the chief scientist of the Digital Twin Institute. He's also from the University of Central Florida. Dr. Greaves, as I said, originated the digital twin concept and is internationally recognized as an expert in this domain. And he has written seminal papers about digital twin that you probably all wrote, at least one of them. So, Michael, welcome. And if you would like, I will stop sharing if you would like to share your presentation.
Thank you. Can you hear me?
Yes. Yep.
And you can see my screen, right?
Yes.
Okay. So in the short time that I have here, and I just need to clarify something. The actual digital twin term comes from John Vickers of NASA, who I was working with. I had called it some different things. In fact, NASA had called it some really weird things. But the digital twin name comes from NASA. It is my concept, and so I'm going to start talking about the fact that the replication, prediction, and impact, I think, captures pretty well what it is that we're trying to do. We're trying to in essence capture the information so that we can replicate, in fact, capture history. We want to predict, which impact is a form of prediction. The thing I need to sort of start off with is that one of the things that I caution people about is the idea of a boil the ocean digital twin project, and quite frankly, in more ways than one, this certainly looks like one. I mean, I'm not sure. In fact, I would certainly like to hear any objection to the fact that you're probably talking about the most complexity of a multi-domain system when we're talking about the environment. I mean, I deal a lot with very complex systems like spaceships and aircraft carriers, and I mean, even contend that the patient biology is not as complex as the thing that you're trying to attack here. I think one of the critical issues that you guys need to consider is the need for a validation of your data models and presentation. I think that what you're going to have to do when I talk about interoperability in a second is pull together all these kind of different interdisciplinary modules. And if I look at the list of your reports, you know, it's wildfires, ocean carbon, water cycle, atmosphere boundary level, and those sorts of things are going to have to be connected in this interoperability thing, which I will talk on my next slide. What I think you really need to think about is independent, unbiased audits, reports, and ratings that mirror the financial world in terms of how well are your models doing. And it's no good to do predictions and impact if they are wildly inaccurate when you move ahead. I mean, one of the opportunities of digital twin is we're time unconstrained, and so we can do predictions with our own time frame. But if it doesn't match what actually is happening, then I'm not sure why we would give that any credibility. I think you need red team validation of new models. I mean, I think the fact that I mean, the papers that I've taken a look at, and I will say that I am by no means even a neophyte in this area, is it seems that people come up with their own models, and do they connect into the rest of the system? Who knows? We ought to have, you know, an audit of data integrity and consistency. Are we getting the right data, and does it have the same integrity and consistency so that we can rely on timeline trends? Prediction and impact accuracy and reliability. So there ought to be, at the end of sort of each period, an audit report that said how well did we do, and those models that are found wanting need to be either addressed or discarded for other models. I mean, the whole idea about science is, can I predict, and does it have any accuracy? And finally, I think that you need neutral representation. You know, I see language about extreme and colors of red, and I think that detracts from the scientific objectivity and unbiasedness that we need. So in terms of digital twin interoperability, which is high on my list of things that I'm concerned about even much lesser systems than this, is that there's a thing called cohesion, which is the fact that everything interoperates and is consistent across the entire system. And interoperability requires cohesion for internals. So individual digital twins need to have internal cohesion. So if I change one parameter, for example, the one I like to use, if I lengthen a steel beam, the weight has to increase. If I basically put fuel into an airplane, the entire weight of the airplane has to go up. And then externally, which is a much bigger problem, is we have multiple digital twins that need to be addressed. So cohesion enforcement gets done kind of one of two ways here, depending on whether I'm in the physical universe or whether I'm in a virtual one. In terms of the physical universe, it's easy. The material forces enforce that. So the atoms do their job, and no matter how much we'd like them to do something different, they are going to enforce cohesion. And so we have this automatic physical enforcement. The issue is when we move into the virtual, we now have information inputs and digital processing that we actually have to do ourselves in order to enforce cohesion. And we have the utmost opportunity to either do that or not do that. And in point of fact, if we don't really understand what the cause and effect here is and rely on correlation or even worse, just a theory, we wind up with models that will not predict the future. So here's potential digital twin cohesions. And I know we've talked about standards, but standards are awfully tough to come by, especially in very complex systems, and it takes a long time to do it. I mean, the first is ad hoc programming. So in essence, we're aware of what the requirements are, and we brute force program the different systems to interact with each other. We do have standards. So you're talking about ontologies, attributes, method call semantics to make these different systems work together. So federated systems have to have these, for want of a better term, call them APIs, that allow us to integrate these different systems for all the aspects that we need. So we need to make sure we have the right inputs and the right outputs. Harmonization, which is a little easier. So we have groups that get together to decide how they're going to harmonize their different systems and work together to do that. Much faster than standards, but obviously not as comprehensive. And you can, in essence, get into the islands of incompatibility. Middleware, so developing a platform. So do you have one group that develops an entire platform that's going to basically be able to adhere to this? I've got a book I'm working on with a metaverse kind of thing, and so do we have metaverses that, in essence, enforce all the physical rules of the universe? It's kind of daunting, but do we have to go there because of the complexity? And so they will develop into different platforms that we may use for different things. One of my latest kind of ideas is the fact that this may be where AI comes into play in terms of AI looking at the various different systems and looking at their inputs and outputs and being able to in essence harmonize this. But if you're going to have an integrated system that in essence mirrors what the environment is, you're going to have to address this interoperability, and how you address it along with this capability of making sure that you're relying on models that actually do predict, I think is some of the big challenges that you're going to face. So with that, I will stop on sharing and turn it back to you, Jacqueline.
Thank you very much. This was a really, really nice introduction. So I propose that we keep all the questions at the end of all the presentations.